Okay, I've started recording. Once again, is there a question? Okay, today, I think I plan on doing a couple of things. One is that I plan to review a couple of things. And I'll say something about Monte Carlo simulations. I hope that somebody will say, please explain this or that, and then I will try to explain this or that. All right, well, let me start the review now. The main theorem of linear algebra, and I might mention that so far most working theoretical physicists, including high-energy theoretical physicists, don't know the singular value decomposition, and so they stumble around with a kludge that's a close approximation to it. The singular value decomposition, as I said, is the main theorem of linear algebra, and what it says is that every complex rectangular matrix doesn't need to be square, is the product of a unitary matrix, a rectangular matrix that only has a diagonal, and then another unitary matrix. So in other words, a matrix that might look like this will be equal to some unitary matrix that looks like that, some matrix that has positive numbers on the diagonal, that's sigma. The unitary matrix here is U. So this is A, and it's going to equal U sigma V dagger. And then we'll have a whoops, big mistake there. Let me just get rid of that. This would be a unitary matrix that V dagger. One, for technical reasons, one uses V dagger rather than V. And so this rectangular matrix has a diagonal, and the positive values on the diagonal are called the singular values. And so that's the, as I said, the fundamental theorem of linear algebra. If we skip to, well, vector calculus, I don't know if there's anything in vector calculus that's really needs reviewing. Those are basically formulas that describe, that define gradient, divergence, and curl and Laplacian, and show what they are in different coordinate systems. The three principal coordinate systems being rectangular, cylindrical, and spherical. If we jump to Fourier series, the main thing about Fourier series is the orthonormality of these phase factors divided by square root of 2 pi. That allows us to expand a wide variety, to approximate a wide variety of functions as constants times these phase factors summed over all integers. And the orthonormality relation then allows you to identify the coefficient n as the integral of the function over the interval divided by, with the opposite phase factor and divided by square root of 2 pi. That is the main thing about Fourier series. For Fourier transforms, it's as we saw in the beginning of the discussion of Fourier transforms. If you take the Fourier series representation of a function and the formula for the coefficients Fn, and then you let L go to infinity, you see that these, you're essentially summing over an infinite, well, you're always summing over an infinite set of phase factors, but as L goes to infinity, the density of those phase factors increases. So in other words, you have e to the I 2 pi n over L times x. But then the next one is e to the I 2 pi n plus 1 over L x. And the difference in phase of these two phase factors is e to the I 2 pi over Lx. So that difference in phase is, this is almost equal to 1. It's 1 plus I 2 pi over L times x. And since you're letting L go to infinity, these are very dense phase factors. One of the things that we learned about in the case of when we were looking at Fourier transforms is that if you combine the Fourier transform together with the formula for its inverse, namely f tilde is this integral, you combine them together, you get an expression for Dirac's delta function. Namely, it's an integral over all k of a phase factor e to the I kx minus y. And here, for example, is up to 350,000 is the vertical axis, and the x-axis is 2 times 10 to the minus 3. The chapter on infinite series, I suppose the most important thing was the generalization of factorials, namely that the factorial can be generalized from integers to complex numbers, and then the z factorial is the integral from 0 to infinity of e to the minus t to the z dt. That shows you that 0 factorial has to be 1. And unfortunately, the gamma function is defined as z minus 1 factorial. Who ordered the minus 1? I don't know. I think it's caused more headaches than, well, let's just say it's caused an awful lot of headaches. Another formula is that z factorial is gamma of z plus 1. And the gamma function is defined everywhere in the complex plane except at 0 and the negative integers. So you see, if gamma is 0, you've got an integral that is e to the minus t dt over t. That 1 over t gives you a log singularity at t equals 0. So the gamma function then is analytic everywhere except at the negative integers. So maybe I should draw a little picture of that. We draw the complex plane gamma of z. Its fine everywhere except at -1, -2, -3.
All right, would you mind making sure that we can see the board real quick?
Yeah, thank you. I always forget to do that. Just to repeat what the gamma function is, gamma of z is an integral from 0 to infinity, e to the minus t, t to the z minus 1 dt, and that's equal to z minus 1 factorial. And oh, I'm sorry, I left out the fact that if we're doing gamma of z, then it's also bad at z equals 0. So hold on, let me put an x here. So it's gamma of z is bad at 0 and at the negative integers. But it's analytic everywhere else. So that's the main thing of that chapter. Now, for the chapter of on complex variable theory, the main thing, well, it's funny, the main thing, I guess, is that I squared is -1, and that we can define a complex number z as equal to x plus iy. Let me move this over so you get to see it. Well, I can't expand it for some silly reason. We then say that if we have some function f of z, or equivalently f of x and y, or equivalently f of x plus iy, now then we can compute something, we can try to compute something called its derivative, and that would be a limit as z prime approaches z of f of z prime minus f of z divided by z prime minus z. Now, if this exists, no matter how one approaches z prime, no matter how z prime approaches z, so z is here, say, whether it approaches like that or like this or like that or down this way, if this limit exists, no matter how z prime approaches z, then we say that the function is differentiable at z. And if it's differentiable in a disk around z, then we say it's analytic or holomorphic at z. Many of the simple functions, polynomials, exponentials, are analytic, in fact, analytic everywhere. Now, one thing that we learned was that we can apply this definition to derive a criterion for, we have a function f of x, y that's u of x and y plus I times v of x and y. Then there's a criterion. There's a criterion for, well, there are two criteria actually, for whether the function's analytic, and namely it is that if u sub x, which is the x derivative of u, is equal to v sub y, which of course is the y derivative of v, and if v sub x is equal to minus uy. So these two derivative conditions are called the Cauchy-Riemann conditions, and if they're satisfied, then the function is differentiable at the point that, at which you evaluate them, the conditions, or find that they're satisfied, and you know, in a disk and so forth. It's usually usually when you apply the Cauchy-Riemann conditions, you find that they're either true everywhere or true almost everywhere. It's rare that they're just true at a point. All right, let me see what follows from that, of course, is that the integral of an analytic function in any closed contour is 0. As long as it's inside a region, as long as the region inside, so this region, it has to be analytic on the surface, on the curve, of course, that's the contour C, and it has to be analytic inside the contour. And in that case, the integral vanishes. Well, functions are vectors. So there was a question, can you do the Gram-Schmidt for functions rather than vectors? Functions are vectors. You can multiply two functions, let us say ax plus bx squared. So you can add functions together, you can multiply them by numbers, and so they form a vector space. So functions are vectors. Remember, in the very beginning here, vectors are things that can be multiplied by numbers and added together to form other vectors in the same vector space. And one example is a hardware store, the inventory of a hardware store. It's a vector space over the natural numbers plus 0. So let's go back to, so one of the things that follows from Cauchy's integral theorem, let's see, I always forget names. So Cauchy's integral theorem basically is what I wrote down, namely that the integral along any closed contour of f of z dz is 0 as long as the contour C lies inside a region in which the function is totally analytic over the whole region. Now, it doesn't, it's immaterial how well, how generously the region of analyticity encloses the curve. It could be, for example, that the region of analyticity just sort of extends.
All right, one more time. Can you make sure the screen is visible?
Yeah, damn it. Sorry about that. So let me review this. So these are the Cauchy-Riemann conditions, and this is Cauchy's integral theorem. And the deal is that the function, the integral along a closed contour of an analytic function vanishes as long as the contour and the region inside the contour lie inside a region in which the function's analytic. So cases where that isn't, where you don't get zero is, for example, if you have a contour like this, and there might be a singularity here or there, or even a whole region where the thing is singular, then Cauchy's integral formula no longer holds. Now, what we found was that Cauchy's integral theorem could be used to derive Cauchy's integral formula, which is 642 here. And that's basically that f of, there I wrote f of z0, so I guess I might as well write it again. Turns out to be 1 over 2 pi I, an integral along a closed contour, f of z over z minus z0 dz. And so what are the technical aspects of this? The technical aspects of this are that, let us say this is the contour. Whoops. All right, let me first get rid of this contour. So here's our contour. I don't know why I drew it like that. So this is the contour. Let's say that Z0, damn it. Let me first get rid of that stupid one. Let's say Z0 is here. Z0, let us say, is there. And so the important thing is that the contour go counterclockwise about the point Z0. And you remember when we talked about integral transforms, or let me try to remember what the term was. Integral equations and integral transformations. We mentioned 1 over z minus z0 as one of the choices for, I think we called it K, a kernel in an integral transformation. And Cauchy's integral formula uses 1 over z minus z0 to represent a function. Now, the other proviso here is that this whole thing is in a region of analyticity, and the deal is that the only that the function f is analytic entirely within the curve, the yellow curve, let us say. And you can then differentiate Cauchy's integral formula, and when you do, you then get a generalization, which is dn d z to the n of f of z, which I wrote there as fn of z, is n factorial over 2 pi I integral f of z prime dz prime over z prime minus z to the n plus, Jesus, n plus 1. So that's equation 646. And once again, for this to hold, at this point, what we've got is a, let us say, a curve C that in circles a point Z, and the integral is counterclockwise around Z, and but the kernel now is 1 over 1 over Z prime minus Z to the n plus 1. So this is a different choice for the kernel. Kernel is spelled with a K because it came from the German. German was the language of science until the end of the Second World War. I expect that in another 50 years, at the latest, Chinese will be the language of science. All right, so let's see. What else is important here? Well, I think those are the key things for complex variable theory. The other things, of course, are worth knowing about and so forth. For integral equations, what we learned was that you can take a differential equation and use one of Cauchy's tricks and convert it to an integral equation. And then there is a certain amount of nomenclature associated with integral equations. There are Fredholm and Volterra integral equations. The more general case is Fredholm. Volterra just means that the kernel vanishes when x is less than y. And then so let's see, the Fredholm equation of the first kind is just this one. Inhomogeneous of the first kind is that one. Homogeneous of the second kind is this one, and inhomogeneous of the second kind is that one. So that's basically that. I mentioned something about numerical applications. That's the nice thing about integral equations. Differential equations are much more familiar to us because we learn about derivatives, and when we learn about integrals, we typically get tense because we know that integration is so much harder than differentiation. But integrals, when you have an integral equation, you have something that is intrinsically smoother and more amenable to mathematical analysis, and in particular to numerical analysis, because this thing is really just can be thought of as shorthand for a linear algebra problem. Instead of an integral dw, you can imagine it as a sum over various points w times intervals dw, and so this is a linear matrix equation. And then we noticed that we could take a differential equation, turn it into a particular kind of integral equation, and then in particular, if we chose a kernel k equal to, that was a Fourier kernel or a Laplace kernel or a Cauchy kernel, or that's called an Euler kernel, it turns out, we would get well, very useful things: Fourier transforms, Laplace transforms, and Cauchy's integral formula. And moreover, what you can do is, by doing that, you can find solutions of, you can find, if you have a complicated differential equation, you can find that you can find solutions of the complicated differential equation defined in terms of solutions to a much simpler differential equation. And that's been done for the Henkel functions. All right, I think there's more than enough about them. Legendre polynomials, well, basically it's that they're all defined to be orthonormal in the sense that their integral vanishes, the integral from -1 to 1 of the product vanishes if n is not equal to m, and the p-ends of 1, which is the right end of the interval, are all required to be unity. And so that was the basic thing that we learned. Then there's Rodriguez's formula, which is really provides a very convenient way of thinking about and computing Legendre polynomials. What else? Oh, there's a generating function for them. And frankly, I always, whenever I see a generating function, I say to myself, my God, I could never figure that out. I just find generating functions positively remarkable. What else? Oh, yes, orthogonal polynomials. Rodriguez undoubtedly generalized his method beyond Legendre polynomials and invented just whole families of orthogonal polynomials. We then have this, let me just remind you of what these things are. A Legendre polynomial in cosine of theta is occurs in solutions of Laplace's equation in 2 and 3 dimensions. So let me just skip to the, if we're doing it in spherical coordinates, then we have spherical Bessel functions, either the J's or the Y's. Remember, these are infinite at the, these are singular at the origin, these are singular at infinity, singular in the sense that they don't go to 0. This theta is an associated Legendre polynomial in sine and cosine of theta, and phi is just a phase factor, e the im phi. PLM turns out to be the proportional to the mth derivative of the Lth Legendre polynomial multiplied by a funny factor. And the way these occur often in physics problems is as sine to the m of theta dm d cosine theta, the mth derivative of cosine theta of PL of cosine theta. In the Rodriguez form, they look like that. And the spherical harmonics then are theta times phi, where theta has this crazy square root and phi just looks like this. And the square root assures orthonormality of the spherical harmonics over the unit sphere. And so these are the things we use in physics all the time. The next topic that we discussed were Bessel functions. It's traditional to start talking about Bessel functions in terms of the capital J's. Oh, I don't know. I mean, I was the one who basically suggested covers for the book, and I don't remember anything else that I found particularly suggestive. Anyway, I think that the right way to structure the Bessel functions is to start with the spherical Bessel functions, which are simple, and then go to the cylindrical ones. I think, however, that almost all books do it the way I did it. I was about following those books. And so Jn of z is given by this infinite series. It's powers of z squared. And it's very, very rapidly convergent. At the origin, Jn of z is z to the n. over 2 to the n factorial. On the other hand, these alternating signs mean that at large z, it's a trigonometric function. It's proportional to a cosine apart from 1 over square root of z. The j's, because they are functions of z and because they're so convergent, these are entire functions. They're analytic everywhere. They obey Bessel's equation. This is what they look like. J0 is 1 and when rho equals 0. All the others for integer values vanish it. And on the other hand, the others all vanish at rho equals 0. And you can see that they get more and more wavy as z increases. There's this remarkable generating function for the cylindrical Bessel functions. And one can derive integral representations for them, and one gets various rules. Jn of z is j minus n of minus z, and that's minus 1 to the n j minus n of z. So n to minus n is just minus 1 to the n for the cylindrical Bessel functions. There are various recursion relations. And when one applies them to a physical problem, let me just mention this. Remember the Bessel function was a Jn it involves m plus n factorial. Well, you can go from factorial to gamma function by writing it as gamma of m plus n plus 1. That's n factorial. But now, once you have it as a gamma function, you can have nu be essentially any complex number as long as this argument here isn't 0 or a negative integer. And so essentially for the whole complex plane, except for a few points, well, not a few, but except for a discrete set of points, this is well-defined. And in fact, it's probably analytic in nu. But going back to integer values, the Bessel's, if you write rho equal to or z equal to kx, then Bessel's equation looks like this. And this extra parameter here you can think of as an eigenvalue. X you can think of as a weight function. And this is then the self-adjoint form. And we want these boundary conditions, namely this thing vanish at the two ends of the interval. And the interval typically for Bessel functions is between 0 and some number b. Okay, there's a question. Well, I mean, the generating functions are incredibly useful. What we just saw in the case of Legendre polynomials is that Bessel function, or in terms of Bessel functions, this relation here, exercise 10.5, I don't know if I assigned this, but you can derive the series expansion 10.1 from this Bessel function, from this expression. So in other words, the generating function defines in one simple equation all of the cylindrical Bessel functions. It also gives this integral representation, which was that one, which again is this. And then if you differentiate the generating function, you get all sorts of recursion relations. And the same is true in general, that a generating function defines a whole family of special functions and allows you to prove many properties of those special functions. All right, now let's see, where was I? Since we have a self-adjoint differential system on an interval from 0 to b, and since the eigenvalues k squared are m pi squared over b squared, where m goes from I guess, 1 to infinity, these eigenvalues go to infinity, and so the Bessel functions are complete. Their orthonormality relation, there are 2 ways of writing it, one in terms of the j's and one in terms of the derivatives of the j's. The advantage of the derivative of the j representation is that you have the same n in all 3 cases, whereas if you use just j, it's j sub n plus 1. Anyway, we learned that when you do have a self-adjoint differential system with eigenvalues that go to infinity, then these functions are complete, and the completeness relation for Jn then takes this form. So you're summing over all the eigenvalues. You divide by something that normalizes the functions. And so in this case, it's a b and a Jn. That's the b there. And then you take the weight function raised to the power unity. And so, and you can evaluate it at x or y. So you have x to the alpha and y to the 1 minus alpha. So this is the formula for Dirac's delta function. If you set n equal to 1 and b equal to 1, you then get a somewhat simpler form. And I plotted this using MATLAB. These delta function relations are as remarkable, maybe not as remarkable, they're remarkable, just as the generating functions are remarkable. And the nice thing about the delta function is that you can represent it with a MATLAB or a figure. It turns out that we can think of this as a sort of Fourier series. Because they're complete, you can write f of x in terms of the jn's with coefficients, and then the coefficients are given by this integral. And the analog of, here's the orthogonality or orthonormality relation for the Bessel functions of index n on a finite interval 0 to b. But if you do an infinite interval 0 to infinity, then the orthonormality relation involves a delta function, because on an infinite interval, the eigenvalues are continuous. And so then one has an integral that looks like this. And these can be generalized to complex nu. Okay, we did Bessel's drum as an example. The Bessel functions of the second kind are called, sometimes called Neumann functions. They're sometimes written as capital N rather than capital Y. Anyway, they are the ones that are infinite for small values of z. And if nu is not an integer, then this is a perfectly fine definition of the Bessel function of the second kind, y nu of z. But as nu approaches an integer, you get 0 over 0. And so what you do is you approximate this for nu very close to an integer. And then what you get is basically, maybe I should write this down just to make it a little bit clearer and get this out of the way. Then what we have here is so let us just say that y nu of z is something I'll call numerator of z. sub nu divided by denominator nu of z. But now as nu goes to 0, this becomes 0 plus, let us say, z minus n. Let's say as nu approaches, oh, no, I'm sorry, this was a mistake. It's not z. It's nu minus n times n prime nu of z divided by nu minus n. That's a nu. Oh, God. All right, hold on. Let me just try to write it better. Nu minus n d prime nu of z, where nu prime nu of z is d n nu of z, d nu. The same thing for d. So what you're doing is you write these then, in other words, as you say that y nu of z is then n prime of nu of z divided by d prime nu of z as nu goes to n. So these factors here, these two factors cancel. And this is because what I've, maybe I shouldn't, hold on, let me make this a little better. So this would be equal, this would be equal to 0 plus nu prime, whoops, nu prime minus n prime, well, it's a derivative with respect to nu, but evaluated at n now. And so in other words, yn of z is the numerator derivative evaluated at n divided by of z, the denominator evaluated at n, derivative evaluated at n. And there, the numerator, of course, is cosine pi nu j nu of z minus j of minus nu of z, and the denominator is nu of z, say, is just sine pi nu. Okay, I think that's enough for that Bessel function of the second kind. So these are the guys that are infinite at the origin. And okay, there are two questions there. One is, do generating functions have generating functions? I don't think so, but I don't know. I don't think so, though. Next, where do generating functions come from? Well, I don't really know. As I said to you all many times, I'm amazed whenever I see a generating function, and I find them very humbling because every time I see one, I realize that I never would have figured that out. So I think in mathematics, there are many miracles, and generating functions are one set of miracles. Okay, Bessel functions of the third kind. These are the Henkel functions, and I think we've seen enough about the Henkel functions. The ones of the second kind, these are all infinite at the origin, but they then turn into trigonometric functions at large z, and in particular, the y nu is a 1 over square root of z sine of z, apart from a phase. So then we get to the nice Bessel functions, which are the spherical Bessel functions of the first kind, and they're 1 over square root of x times j of L plus a half. And in particular, let me just emphasize that JL, I tried to do this in LaTeX and couldn't figure out how to do it. It's basically pi over Jesus Christ. Pi over 2x times j, and it's L plus 1/2. It's not L plus 1 divided by 2. Let me get rid of some of this here. At x, of course. So it's basically that it's something quite remarkable. It's that if you take a cylindrical Bessel function, which is very complicated, this infinite series, and you shift the index from L, an integer, to L plus a half, and then divide by the square root of x, you then get something that's much simpler. And the simplicity of these, well, you get something that satisfies the spherical Bessel function differential equation. And in particular, the reason I say that you get something that's simple is that Rowley derived a formula for them, and they're just derivatives of sine x over x, differentiated in this funny way. And these things are current solutions of Helmholtz's equation in 3 dimensions. Well, V here is not a potential, it's the solution. I don't know why I used V as a function. It probably should have been something else. Let me try to make a note to myself. That is kind of a silly notation. V is usually a potential. So as we've seen, what you do to solve Helmholtz's equation in 3 dimensions is you write it as R theta phi. Phi is just this simple thing. Theta is the associated Legendre polynomial in sine and cosine of theta. The product is a spherical harmonic, at least with the right proportionality factor. And then this R has to satisfy a certain differential equation. And well, the R is a spherical Bessel function. Rayleigh's formula leads to a recursion relation, and you also find from Rayleigh's formula what the spherical Bessel function looks like at small x and large x. For small x, what you do is, well, let's see, I'm saying here that you get it from the definition of Jn and the formula for the spherical Bessel function. But I think, in fact, one can see what it is. If it's at small x, you want as few powers of x as possible. And so what you do is let's see, let me do the other case. To see how JL behaves for large rho, what you do is you let the derivatives act on the sign. And then you find, because when they act on rho, you get extra powers of 1 over rho. And so you just have them x on the sign, and then you get this expression for spherical Bessel functions, f a function at large rho. So what we can do for to get this formula is have this act not on the sign, but to act on the 1 over x term. And so then these x's are all going to cancel, and we're going to have let me see, we're going to have 1 over x to the L plus 1. Somehow that's not working out. I thought it would work out. Well, I don't know, I'm missing something. In any event, the Bessel function at JL at small rho is rho to the L. And at large rho, it's sine rho over rho. The self-adjoint differential equation form of Bessel's equation for a spherical Bessel function is this: the eigenvalue is k squared, the weight function is r squared. JL vanishes at its zeros. This defines what ZL, and L is this L, and N goes from first zero, second zero, third zero, and so forth. And so what one does is you have an interval from 0 to a, then you set k, the eigenvalue, equal to ZLN over a. And then for r equals a, the thing vanishes. And so for any L, you have an infinite set of eigenvalues and eigenfunctions, namely JL of ZL comma M R over A. So the eigenfunction and the eigenvalue are labeled by ZLM, and they vary because you're keeping L constant and varying M. And the relation is this, and that gives you this as a delta function. And you can also expand an arbitrary function in terms of the delta of the spherical Bessel functions. And you then can write the coefficients like this. This is expansion on an interval, a finite interval. On an interval, infinite interval, you have relations that are analogous to those for the cylindrical Bessel functions, namely that JL of KR, JL of K prime R, R squared dr, remember R squared is the weight function, is delta K minus K prime. And well, then there was a Schwinger trick. So this is all kind of special. So I'm going to skip this. Right. Let's see. Is that it? Right. Okay. That's enough for that review. So what I said I'd do today, because mainly I wanted to answer questions. So far, we only got a couple of questions. Let me actually jump then to Monte Carlo methods, because people wanted to see something about it. Now, the Monte Carlo method, one of the nice things about it is that it's simple. It's robust in the sense that it basically kind of always works, as long as you don't make a mistake. And it's useful because it applies so very, very broadly. So for example, one of the simplest cases is, suppose you want to just numerically integrate a function, and the Monte Carlo method is used, and let me say, what do I want to say? I want to say that it's most useful when you're integrating over more than one variable. If you're integrating a function, in other words, if you're just, face and key, for God's sakes. So let me just, let's see, put it this way. If you're just trying to compute an integral I, which is an integral from a to b of some f of x dx, well, you can just write a computer program and discretize this and write this as 1 over n sum f of xi, I equals 1 to capital N, and you then you can then just do that sum, and you can set xi equal to, well, it's basically something like I over b minus a, something like that. And you don't really need a Monte Carlo method. The Monte Carlo method comes into its own when it becomes really useful when you're integrating a function that's not a function of a single variable, but instead you're integrating over some region, and you're integrating a function f of x1, x2, up to x, what did I call it, little n, dnx, and imagine that n is equal to, let us say, 10 to the fourth or 100 to the fourth. Okay, so then you're dealing with a problem that really requires Monte Carlo integration, because you can't just sum over all the lattice points. In 1 dimension and 2 dimensions, you can sum over all the lattice points. But if you have 10 to the fourth dimensions, now you might say, why do you have 10 to the fourth or 100 to the fourth? Well, suppose you take space-time and represent it as a lattice, then you have x1 going this way, x2 going this way, x3 going that way. Oh, Jesus Christ. So you have x3 going this way, and x4, which is time, apart from a c, going some other way. And, you know, we're in 4-dimensional space in that case. And Apple hasn't come out with 4-dimensional iPads yet. Anyway, if you just want 10 points in the x direction and 10 points in the y direction, and then 10 points in the z direction, and then 10 points in the time direction, you're right at 10 to the fourth immediately. And that's not a very good approximation. After all, if you were doing this integral up here, you wouldn't be satisfied with 10 points or even 100 points. You'd use 1,000,000 points. And the computation would be done in a fraction of a second. But if instead of using 1,000,000, you've got to use 10 to the fourth points, or I'm sorry, there are 10 to the fourth dimensions, and you wanted to have, suppose you wanted to have 1,000,000 points in each dimension, then you would have 10 to the sixth raised to the power 10 to the fourth, which is to say 10 to the sixth times 10 to the fourth, and that's, you know, an absurd number of points. So the idea of doing this in this way just does not work. Nonetheless, if you're just integrating over a few dimensions, you could do this. And in that case, the integral formula that I would quote would be 16.3. Then the integral over some region of f of x dn of x is then approximated by ln. We're putting in a box of side L, the region R, some funny region like this, and we're putting it in a box of side L, and we're dividing by the number of points, and then we just sum k equals 1 and to n sub r f of xk. And what I want to say here is you pick random values of x, and so you get points all over here. And some of these points are inside the region R. So this is the region R. Whoops, damn it. This is the region R. Oh, what happened? Now, why did that switch to the damned eraser? So this is the region R. And so you count in this sum here only points that actually fall inside the region. If your random number generator gives you points outside here, you don't count them. And altogether, you keep track of how many points fell inside the region n sub r, and so this is your estimate. Okay, so well, and I gave an example of this, and you can find the actual programs there that do this. There's a more sophisticated way to do it. By the way, I said random numbers. The basic concept is, the technical term is pseudo-random numbers. Pseudo-random numbers. And there are scripts or programs that generate pseudo-random numbers. And since they're generated from a script, they're not truly random, but the idea is that they essentially don't have any, there's no correlation that one can find or can imagine, or if there is any correlation, it's so bizarre that it's not going to affect your physics in any way. There's something better than pseudo-random numbers, though, and these are what are called quasi-random numbers. And the example is here's an example. These are, for example, Halton sequences. And this is a Halton sequence of base 2. This is a Halton sequence of base 3. And then there are others that were invented by, I think, a Russian by the name of Sobol. I'm not sure he was Russian. He might have been Ukrainian or Czech or whatever. Anyway, if you use pseudo-random numbers, then your errors go down like 1 over square root of n. If you use quasi-random numbers, which are more uniform, your errors go down like 1 over n to the 2/3 or 1 over n even, where n is the number of points that you actually, there are a number of random points that you sum over. We can talk about applications to experiments, and we can imagine one application of Monte Carlo simulations to experiments is to see decide whether a signal is due to a defect in the detector or to a random fluctuation in the real events. or to some new and unexpected phenomenon. And typically, I don't think one can distinguish between those three cases. What the mathematics can do is tell you whether a particular signal is weird and that you need to investigate it and figure out whether it's that the detector is wrong or it's some crazy fluctuation or some new phenomenon. And of course, that requires probably another experiment or a detailed analysis of what's going on. So let's assume that background can be ignored and that real events arrive randomly in time and apart from extraordinary phenomena. And what you do is you write a Monte Carlo program that generates the kind of real random events to which your detector is sensitive, and then to use these events to compute the probability that the unusual signal occurred randomly. And so let's consider the case of cosmic rays. These are protons or nuclei that shoot through space at some fraction of the speed of light. And when they enter the Earth's atmosphere, they typically collide with the nucleus of or with the electrons of an atom or a molecule, typically a nitrogen molecule in the atmosphere. And if they hit the nucleus, then they make a shower of pions. Actually, they could even shower pions if they hit an electron, but let's stick with the nucleus. Anyway, these pions, you then get a, so let me switch to maybe some other color. So you have, for example, a pi plus, which will decay into a mu plus, plus a new mu. And then the mu plus will decay into a positron plus an anti-mu neutrino plus an electron neutrino. And so what can happen? Well, this electron neutrino could, so this happens way up in the upper atmosphere. So here is a, let us say a proton comes along, hits a nitrogen nucleus, and we get a shower of pions. Then the pions decay into muons and neutrinos. And here, let me get rid of this. Is that N? Well, that's a mu. All right, it's just a badly written mu. And then these neutrinos, so this neutrino can come down and you can have, here's the Earth, and you can have an underground detector here. And your little detector is sitting here in a cave underground, and occasionally a neutrino will go through and hit the detector. And in the detector, it might produce a muon. So for example, a mu neutrino interacting with an electron can go to a, Jesus Christ, can go to a muon plus an electron neutrino. And this muon then could be detected in your detector. And if we had gone through chapter 15, which is about probability and statistics, we'd realize that the probability here of detecting n muons in a certain period of time, say per day, if the average number of muons per day is n with funny brackets, then this is what's called a Poisson distribution. One expects it to be Poisson, and it looks like this. So this is the kind of probability distribution that you expect if these are just random muons created by random electrons. Okay, well, we seem to be just about out of time. It's also a Thursday, so you have plenty of time to think about sending me an email over the weekend or on Monday and tell me what you'd like me to do on Tuesday. Shall I do more about Monte Carlos? And then if we finish Monte Carlo, what shall I do? I think some relativity would be a good idea. Another possibility is probability and statistics, because at this stage, unless you've had a course on probability and statistics, the reason why this is a Poisson distribution might be mysterious. All right, well, we're out of time. I will take this and put it on YouTube, and I will add, I'll send this thing to the, this is the tail end of a very long note, and I just, so those, both the note file, some of the note files and some of the example files, they grow with time. So if you last looked at one of them 2 or 3 weeks ago and you look at it again, you'll be surprised that it's twice as long. And so there's all sorts of new material. All right, so I'll say good night to all of you. Stay safe and be careful not to get sick, because this is this can be a very serious illness. And moreover, if you get sick, you'll probably infect somebody else, in fact, possibly several people. So keep yourself and your friends safe. Remember, it's transmitted through the air. And so being indoors with people you don't know is dangerous. All right, so I'm going to end the thing now. So I'm going to stop share.
Thank you very much.
Thank you.